get us started here. And maybe I will begin by saying the last class, we tried to incorporate both chapters 7 and 8 in one big clump. You probably noticed it was a lot more mathematical, if you will, than any of the ones we've done in the past. Let me recap to get started here on what we then did on that last lecture, because I think until we start to actually do example problems, which I'm about to do, it doesn't really get the full impact of what we worked out. And so here's what we did. It took us about an hour or more to work it out, but we started off by saying work then would be an integral of the force dotted with the distance moved. And so we spent a little time starting with the definition of work, incorporating that with the more mathematics you have now that you've gone beyond 102. So we had a dot product, which has a trig function in it, and we have an integral in it. And then from there, we said, well, let's look then at the net force and integrate it, because that would be the same as adding up the individual forces, dotting with the distance moved. And so we solved both sides of this equation. We said when you are adding up the forces, there could be many forces. For example, one of them would be the force of gravity. And so we said that if you put in the force of gravity, you would get a negative mgy final plus an mgy initial. And so this was then the work done by gravity. We went on and looked at other forces. Another one we had was a spring. And we said, okay, what if you had a spring involved? And that's where we spent some time talking about Hooke's law. And when we did that one, we came up with a 1/2 kx squared final minus 1/2 kx initial squared. No, actually I guess it was a minus and then minus a negative. And so we had this term, which again, maybe I should call this the work by a spring, or an elastic work might be another word. In fact, I was just going to check with your author. Yeah, he does use the word elastic. Let's see, what other forces did we have in there? Oh, friction. We said there could be the force of friction. And so we came up with a negative force of friction times the distance traveled. And so again, we could say this piece of the puzzle was the work done by friction. That might have been it for the explicit ones. Oh, I think we did have like normal force on there, but we showed that that was 0, so I won't bother to put that one on there. I think we left an open category for other forces that might show up, either this chapter or in future chapters. And so let me just write it as plus, and I'll just call it a W, or a work done by other forces. An example you'll see today will be one with a bullet being pushed down the rifle of a barrel. And so that force comes from the expanding gases of the gunpowder. So I'd say there's an example of another force besides a spring and besides gravity. We might call that later on a chemical energy. Let me adjust this as we get started here. Let's see, and I think that covered everything. 1, 2, 3. Yeah, I think that was it. And then, of course, the other side of the equation was an integral of the net force. And of course, the net force, we took advantage of that being equal to ma, Newton's second law. And when we integrated that, we got 1/2 mv final squared minus 1/2 mv initial squared. So again, I thought I would recap this morning and say, this is what we did. It's a long equation, but it does show the idea of the work. In fact, we didn't stop there. We moved things around. We said, okay, let's take everything with a negative sign. And if you'll notice, all the final stuff has a negative sign and put it over here. And all the initial stuff, let's bring it over to this side. And when you do that, you get on the left-hand side, this term, I'll leave here as a positive. This one, I will leave here. I'll leave this one here, but before I write it, I'm going to move this one over. And then I will pause, because there are the four terms on the left-hand side of the equation. And if you look closely at those four terms, what they are really saying is these are the initial conditions, aren't they? Maybe leaving this one off for just a second, because that's something that may or may not happen in a particular problem. But this is saying, what is the initial? And so let's give some names here. We're going to call this the potential energy. More specifically, the gravitational potential energy. So what is the initial gravitational potential energy? Let's give this a name. Let's call it the elastic potential energy. But again, notice it's initial. Let's give this a name. Since it has to do with motion, let's call it kinetic. So we'll call that a kinetic energy. And so what you are saying in this part of the equation is this is all the energies initially, before something happens. This is the energy at that particular moment. What is it equal to? Well, now as I take that negative and that negative and that negative, and this one's already over there, and move them to that side, I would have mgy final, 1/2 kx final squared, 1/2 mv final squared, force of friction times distance. And so notice these are the four terms that are after something happens. And so again, look at it. This would again be the gravitational potential energy. I would call this the final gravitational potential energy. This one, this is the energy in that spring. That's the elastic energy. Now it's after, so it's a final. But it looks like that one. This one, this is how much kinetic energy it has. Again, afterwards. This then is one that I guess I would refer to, let me just call it the heat here. This is the rubbing that goes on. For those of you who remember from your 102, heat is the molecular motion or the kinetic motion of those molecules on a microscopic scale. And so what I really have here is a simple statement that is saying the energy you start with, and including any energy you might add to the system, is then equal to the energy you end with. And so both chapters 7 and 8 are really trying to build up to this grand finale. 7 just does a couple of terms. 8 adds the other terms like heat in there. I'm going to put a box around it and try not to erase it for the rest of today. But there is, you'll see what I'm going to try and illustrate in chapter 7 and chapter 8. It's a principle called conservation of energy. It's the first of our 3 major conservational principles that we've come across this semester. I know you've seen it in other science classes, particularly your Physics 102. It is probably one of the most important physical principles. I don't know, it's hard to debate which is more important, Newton's second law or conservation of energy or conservation of momentum. They're equally important. But the point being is this is going to be a powerful tool. And so watch as I do examples. And so I want to just spend the rest of today using the principle of conservation of energy and put it into applications and so show you how powerful it can be. Good news here is even though we spent a lot of time going through a bunch of fancy mathematics and doing a bunch of integrals, you won't have to do those. We've already done them. Unless, of course, we have some new force that shows up along the way, then we're going to have to actually do the integral because we haven't done the integral for that force yet. And so you'll see that show up a little bit this semester. You will certainly see it a lot in the next semester where we do throw some new forces, both electricity and magnetism next semester. And so we've got to add to this. But hopefully I will get across before today's over how powerful this can be. And so the principle of conservation of energy can be used to solve a lot of problems. I would even say we've now opened up a very interesting door, a very powerful door, but sometimes for students can be a confusing door. If I were to take this pen and hold it up here and drop it and ask, okay, how fast is it going when it hits the ground? Well, depending on what other information you have, you might say, oh, we know the force of gravity. We know Newton's second law. And that's what we've been doing. But couldn't you also figure out how fast it's going by using energy? So you have a choice. Do I approach this problem with Newton's second law? Or do I approach this problem with energy? Obviously, I think the best choice is the one that's going to make the problem the easiest to do. And that will be a condition on what is given in the problem. I think where it gets confusing for students is now you've got to think about what is given, what principles do you know, which one will get me there, and if both will get me there, which one will get me there the easiest. And so it's not just a simple recipe. Do this, do this, do this, do this, get the answer. Now we have more complexity to it. Now when you sit down for test number 2, and more so when we get into the final exam, you have to ask yourself, ooh, what principle am I going to use? The first test, for many of you it was an easy test. Some of you it wasn't quite so easy. But I think one of the things that make the first test easier than the other tests is you knew the first test was all kinematics. No question about it. You got the problem? It's kinematics. How do you do it? Kinematics. What have we studied so far? Kinematics. That's all it was. But now, going into the second test, the question is this a kinematics problem? Is this a Newton's second law or third law type problem? Or is this a conservation of momentum problem? And those will be the choices you'll have to make when you sit down and do test 2. Where by the time you get to test 3, it'll even be more. It'll be like, okay, now, is this a kinematics problem? Is this Newton's laws of motion problem? Is this an energy problem? Or when by the time we get to test 3, is it a momentum problem? Or is it a rotational problem? And so those will be the next 2 big things that we study moving forward. And then, of course, by the time we get to the, well, you see the idea. And by the time we finish next semester, and by the time we finish the 3rd semester, you got to sit down and say, oh my gosh, is this a thermodynamics problem? Is this an optics problem? Is this a mechanics problem? And if it comes out to be a mechanics problem, you say, well, and then how do I do it? Do I use conservation of energy? And so the experience of working through these problems and doing the homework really fits in. And again, it's more of what I've been saying from the beginning. Physics is about knowing how to apply a few very powerful principles to explain a universal phenomenon. There's not many new principles we have. I mean, basically you have 3 now. You have the whole idea of the kinematics, you have Newton's laws of motion, and now we have conservation of energy. And that's it. That will answer everything we've done this whole semester. But of course, the harder part is thinking through the problem and even knowing which principle would be the most appropriate one to do it. And so, like I've said many times in the past, do you want to know the answers to all the problems in Chapter 7? I'll even do you better. You want to know the answer to all the homework problems in 7 and 8? There it is. Got a box on it. It's conservation of energy. Start with that, fill in the details, you're done. It might be 2 hours later before you're done with the first problem, but that will be the whole approach here, okay? So I will start showing you some examples. I do want to say one more little thing before we finish, and there is another word we should probably throw out here. It shows up here in chapter 8, power. We'll use the symbol capital P for power, but here's the definition. It is the rate at work. It is the rate at which work is being performed. You might even say it is the rate at which energy is being either consumed or generated. Whichever way you want to phrase that, power is closely tied to energy. It is not energy itself, it is the rate at which energy is being done. And since you guys know calculus, I will write it in its calculus form. I'll start with asking then, what would be the unit used to measure power? Oh, and actually I just realized, I don't even know if I mentioned the units for work, did I? Well, let me go back one step. Let me come back here. So many of you guys answered it last time, since I know you've seen these units. I did not explicitly ask it, but I should have. What are the units for work? Yeah, it is a force, so that's a Newton. And it's a distance, so that's in meters. So it's a Newton times a meter. And as you guys pointed out last time, at least some of you, just in case there's a few of you who don't know, what do we call a Newton times a meter? Yeah, a joule. And so for those of you who may not be familiar with the metric system, then we have a joule. If you want to remember that a Newton was a kilogram times a meter per second, so when you multiply it by another meter, this would be the breakdown of the units for a joule. But it's useful when our units start to get very complicated, as they are beginning to get now, to give them their own little name. And the tradition is to name them in honor of the great scientists in that field. And so you saw that the first time with the Newton. We took the mass times the acceleration, and we got that. And instead of, writing the units as a kilogram meter per second squared, we just gave it one big name called a Newton in honor of Newton. Now that we are multiplying it by a distance, this is the unit then for work, or the unit for energy. And in honor of joule, we call it just that, a joule. So that being said, let's come over to here and ask, what would be then the units for power? Well, what would go in the numerator? Unit for energy, right? Joule. What would go in the denominator? Seconds, right? If again you wanted to break it into its pieces, we already said that this is a joule, so if you divide that by a second, you're going to get an S cubed. So this is really a kilogram meters squared over seconds cubed. I don't know if that will ever serve us well, but that is what it is equal to. This then is given the name Watt after and in honor of James Watt and the invention of the steam engine and measuring the rate at which work is being done. And so we got Joule and his work on converting calories and units of mechanics to heat, and whole idea of conservation of energy kind of starts and initiates with him. Watt and the steam engine, and so heat engines kind of initiate with Watt. And so these are the honors we get. Maybe I should point out, because I think most of you are familiar already with the word Watt, but unfortunately most of you are familiar with the word Watt when it comes to electrical power. It's still power. If I plug in a light bulb and it consumes 100 joules of electrical energy every second, and then for lights my living room. That is a rating of power. How much energy per second does the light bulb use? Now in that case, it's electrical power. If I put my cold chicken in the microwave and turn it on, and the little dial on the says your microwave is 1,000 watts. Again, it means how much energy does it use every second. But energy does not have to be electrical energy. It could be mechanical energy, which we are dealing with, but we would still call it a watt. So don't fall into the trap thinking that watt is only something that has to do with electricity. That's not true. It may be your first exposure to the watt, but that's not what the watt means. Yeah.
But does it still translate to like units, like the charge and intensity?
Well, let me put it this way. It is still a measure of power, okay? But when I'm dealing with electricity, I would say that power is coming from charges and from current and from voltages. So if I'm working with electricity and I'm dealing with the power in a light bulb, I'm probably also interested in how much current and charge is in that light bulb. On the other hand, if I'm buying a car and I want to know how much power do I get from the engine, and of course in the United States we would probably come across an engine that is listed in horsepower. We would have the older imperial units for it. But if I was buying a car overseas, I would walk up to the window in the dealership, and instead of saying 200 horsepower, it would say, well, whatever 200 times 746, and that's probably what I should put on here. 1 horsepower is 746 watts, meaning 200 horsepower would be, good time to grab my calculator here. So 200 times 746, it would probably be listed that the car is 149 kilowatts. And so that same car overseas would be listed a little different. Instead of 200 horsepower, it would be 149 kilowatts. And it would tell me something about it. But again, I'm afraid too many of us would probably think, oh, if it said the power was in kilowatts, you might think this is an electric car. And it's not necessarily an electric car. Okay? So I'll say it again. Watt is a measure of power. So when it comes to mechanical watts, then I'm going to be interested in things like the force. If I was, say, a force from a spring, I could take a giant spring and pull on a cart. And so I would talk about how much power in terms of the force from the spring and the distance it moved, as opposed to charge and current. Well, hope that all helps. Let me make one more step here, because another way of looking at this equation for power, let me just write it as dW dt. So there is the rate at which work is being done. Let me draw your attention back over to this equation delivered from the engine is applying a certain force on my car while my car is going a certain speed. And so if I thought about power from a mechanical point of view, I would be thinking about its force and its speed. If I was thinking about power from an electrical point of view, I would think about currents and charges. Okay? And so that's the last piece of chapter 8 is really this energy, but the rate at which energy is done. Well, that being said, why don't I turn on the textbook here. Looks like I got number 2 here, and I got a little mark that says simplest problem we could start with. So, all right, well, let's start with here. And I think you'll see the idea here. I'll start with examples in chapter 7. And so let me go to chapter 7 first. And I think we will be able to complete all the examples from chapter 7. And you'll see every example I do in chapter 7 will be basically this equation with not all the pieces in there. Because as I said, this is the grand finale. This is both chapters 7 and 8 put together. And so let's start here with the simplest ones. And so again, same idea. Let me leave that box here and just, where's my wet rag? And let's start working on these. And so this first question is just simply about a raindrop falling out of the sky. And it's asking a few questions about work. It might even have potential energy. I don't think this one has potential energy. It does have some air resistance. And so let's see how it all fits together here. So number 2, let's read it together. And like any problem, that first step is a big one. Get a good understanding of what's going on. Start there, and then start looking at it in terms of energy. Obviously, since it's in chapter 7, we don't have the more difficult part that you are going to have to ask on the test. You know this is an energy question. On the test, you're going to have to say, is this an energy question or is this a Newton's second law question? But this one, I know it's an energy one. In fact, here's what it says. It says, a raindrop has a mass of 3.35 times 10 to the minus 5 kilograms. It falls vertically at a constant speed under the influence of both gravity and air resistance. Modeling this raindrop as a particle, it falls 100 meters. What is the work done on the raindrop by A, gravity, and B, air resistance? All right, maybe it's worth kind of saying, okay, here's my raindrop. Here it is being pulled down by gravity. Here it is being lifted up by the air resistance, the friction. I'm kind of torn on what symbol to use here. Because in chapter 6, for air resistance, didn't we use the R? All right. So from that reason, I want to say, let's use R. But on the other hand, when we kind of worked out this equation, didn't we say F was the friction force? Although, to be quite honest, when we did it, we said, oh, let's only worry about solid-to-solid friction. Well, this is not solid-to-solid friction. However, did you catch something interesting in this problem? The beginning part, it says it is falling vertically at a constant speed. That was an important piece. What does that tell me? Okay, I'm already at terminal velocity. Good, go on. What does that mean? No acceleration. Good. Go on. Forces are equal and opposite. Right. And so all of that is a long way of saying that I know the value of that resistive force. I know it is equal to the weight of the object. And it doesn't go faster or slower. It is at terminal speed. So it means it doesn't change. So this is not like the harder problems that we did in chapter 6 where the air resistance changed as the object was falling because the speed of the object was falling. That all happened earlier on, way up in the sky when it fell. Now, that falling has changed all the way into a constant speed. So maybe this raindrop, this 100 meters, is the last 100 meters before it hits the ground. And, you know, it started way up there. It probably started as ice, actually. All rain no, not all. Nearly all rain starts as ice. And then the resistance, and it melts before it gets down. So we, for better or worse, never see snow here in Santa Barbara. It all melts before it gets down here. But it starts certainly as snow or as a sleet. But it falls down. And so let's look at that last 100 meters. And so this is not the beginning part. This is the end part. And this is a big point right here. That those two have to be equal. Okay? And that fits that first category I keep saying. Got a good understanding of what's going on in this problem? This is not a harder problem where the speed is changing. This is one that it's a constant speed. As you said, it would be at its terminal speed. The acceleration, as you said, would be 0. And as you said, then that means that the resistive force is a constant value equal to the weight of the object. If I know all that, then the rest is pretty easy. Look at the first part of this. How much work is done by gravity? Now, we could go back and redo the integral. Let's not. What did we get for the work done by gravity? Wasn't that the minus mgy final plus mgy initial? I just erased it moments ago. Maybe I should have left it here, but that's how we got this term and that term. This was over here. Those two together was actually then the integral when I took a force of negative mg in the j hat direction, and it moved downward in a, well, actually doesn't have to be upward or downward, but it moved in a y direction. Actually, I guess when we did the integral on Monday, we had the possibility that it could also move in the horizontal direction. But as we argued on Monday, the dot product made the I term or the x term go away, and we ended up with then a minus mgy final minus a negative mgy initial. And there I said I wouldn't do the integral again, and I just did it. Okay? But coming back to the end results here, I can then solve this. But one of the reasons I picked this one first is I made a big deal while we were doing that integral. The reason of going through that is you need to know if you are going to use an equation that has already been set up here for you, what are the conditions that make that equation valid? In other words, what has been chosen already in the process of setting up the equation? And then what has not been chosen. So we remember that we always have freedom of choice, but once chosen, it has power over us. And one of the things I tried to emphasize, and I want to emphasize it again, is, you see that negative right there? What was chosen while we were doing the problem? Down is negative, right. So please keep in mind that I have to call up positive. Some of the other problems we've been doing, we've been calling down positive. Because again, we have that freedom of choice. But using this equation, that choice has already been made. I also made an emphasis that something has not been chosen for us. And that would be the origin. Where does y equal to 0? It hasn't been chosen yet. You could put y equal to 0 anywhere you like. And that's kind of nice, because I would suggest, since this is the equation for the work, we call either the beginning or ending 0. And so drawing this raindrop starting here and going down to there, I'll ask you guys, which one would you like, or where would you like to call y equals to 0? Any choice? The final one? All right. So we will call that 0. So what does that make this? 100. And it has to be a positive 100. Note that if I picked this top part at 0, then what would this have to be? Negative 100. Okay? You'll get the same answer, but you do have to stick to the fact that down is negative, up is positive. So pick your 0, and then if you go up, it's positive. Pick your 0, if you go down, it's negative. So let's do the one you suggest. Let's do this. And so when I come over to here, I would say then that right here I have 0. Because I'm saying the final is 0. And then I would have did I read 3.35 times 10 to the minus something? 5, okay. So I got a little error here, so let me fix that. So 3.35 times 10 to the minus 5. I've got 9.8 for my G, and I've got an initial height of 100. And maybe since this is my first calculation, I should put in my units for each term. And let's talk about units first. This would be a kilogram times a meter times another meter, that's a meter squared, over second squared. What are my units going to be? Yeah, exactly, a joule, right? As it should be, because the units for work are a joule, yeah.
Why is the 9.8 not negative?
Okay, good. Let me emphasize, the G has never been negative. The G represents the number 9.8. Granted, the acceleration is down. The down part is why the negative was here. But the G itself does not have a negative in it. It never has. Go all the way back to chapter 2. And we never put G equals negative 9.8. That was never the case. G has always been positive. So when we had equations like velocity equals initial velocity plus acceleration, and we talked about a falling object, we would put velocity equals to initial, and we said, well, what is the acceleration of a falling object? The answer? Negative G. If G was representing a negative number, we would have put plus G. But we did not do that. Okay, so the 9.8 has always been, still is, a positive number. Okay. Now, notice then, positive, positive, and positive comes out to be positive. Again, if I had put in a negative 9.8, that would have come out to be a negative. We mentioned this last time. What does positive work tell me? Okay. Yeah, remember when we were pulling on that box, if the angle was less than 90 degrees, that was positive work. In other words, if you pull it in the direction it's moving, isn't that positive work? And we know from previous chapters that if you pull something in the direction it's moving, doesn't that tend to make it go faster? Now, don't get me wrong, there might be other forces that are overwhelming your force, making it go faster, so it doesn't actually go faster. But that force by itself would make it go faster. And so the point I wanted you to get out of that discussion, and emphasizing it again now as we're going through the problems, is positive work means it would make the object go faster. If that was the only thing acting on the object, it would go faster. Notice, if gravity was the only thing acting on that raindrop, what would be gravity doing to it? Making it go faster, right. If I did not get a positive number here, I would be very bothered. Work should be positive. This object would be going faster if there was only gravity. Now, we know that there's more than gravity, there's air resistance, and we know it doesn't go faster. For that matter, it doesn't go slower. They say it's at its terminal speed. But I think you get the idea of how the signs go together. And that's a good check. And so I should come out with a positive number, because I know that if there was only this force of gravity, it would make it go faster. And so 3.35 times 10 to the negative 5 for the mass, 9.8, and times 100 comes out to be 0.03. Well, I'll do 3 significant figures. And so there would be the amount of work. Again, notice it is positive. Okay? I'll continue. Part B says how much work was done by the resistance. Okay? Now, I've kind of moved my equation around, but if you remember this term right here, the heat term, the one with the resistance, didn't it start on this side with a negative number? And so, without doing the integral again, I'll just put there. That is what we came out with for the work. And what we are seeing is that because you told me earlier it was at a terminal speed, the force of the friction, which again, maybe this symbol's a little misleading. I did it in terms of solid to solid friction. We don't really have solid to solid friction, but let me just replace this friction with the air resistance, but also let me replace air resistance with what we just said. The air resistance would have to be equal to its weight, and then times the 100 meters that it fell down. I would even go as far to say, I don't even have to get my calculator out for this one. Isn't this mg times 100 the same that we just did right here? Now there is a little difference here. What's different about it? There's a negative in front. So this whole thing's going to be a negative 0.0328 joules of energy. Now, what would the negative be telling me? Yeah, this should tell me that that particular force is making the object slow down. So negative work makes it slow down, positive work makes it speed up, right? So what we have total is what? What would be the total work? 0. Which would tell you what? Total work of 0 means it doesn't speed up, doesn't slow down, right? No acceleration. It keeps its same speed. And that fits perfectly with the description of this problem. And so again, we're looking at motion, we're looking at things, whether they speed up, whether they slow down, or whether they keep the same speed. But it's a different point of view. It's not so much looking at their acceleration, it's looking at their work. Positive work makes it go faster. Negative work makes it slow down. Ultimately, you've got to look at all the work, put all of that together to find out, is it a positive number or a negative number? And if the total work is positive, it would be going faster. If the total work is negative, it would be going slower. Just like in the past chapters, we would have looked at acceleration. And if the acceleration was in the same direction it was moving, we would say it went faster. If the acceleration was opposite to the direction it's moving, we would say it goes slower. And so as we looked at problems and used Newton's laws of motion, we could ask, will it go faster and slower? We can do the same thing. We can look at the energy or the work and say, will it go faster or slower? And that's why this makes a good first problem. It's a very simple one to do. It does not go faster or slower ultimately when both forces are included, and you see that right there. The work is 0. Not faster, not slower. Gravity by itself wants to make it go faster, positive. Friction by itself wants it to go slower, negative. Two together, exactly balanced, and it doesn't go faster, doesn't go slower. Let's try 22. This, like I said, was a good one to get started. 22 takes us a little bit further. 22, must be in the top of this next page here. Here's a good one. This one does fit into this category right here. Work done by something else we haven't talked about. Well, let's work on this one here. 22 says that you have a 100-gram bullet. It is fired from a rifle having a barrel of 0.6 meters long. Choose the origin to be the location where the bullet begins to move. And if you do that, it says the force in newtons created by the expanding gas of the gunpowder is given by this equation. And so I'll write down that equation in a moment. But they give us this long equation to say how much force do you get from this. And so that is what I meant by we have some other forces. I would call this then a chemical energy. The gunpowder itself has a form of energy that is going to push it according to this equation. A, determine the work done by the gases on the bullet as the bullet travels down the length of the barrel. And I'll read B later here, but that's really very clear in terms of what are we asked to do. We are asked to really find this term right here. How much work is done by the expanding gases? And so, as I mentioned a little while ago, all of these terms came from doing an integral. If you ever come across a problem involving those terms, you don't have to redo those integrals. But if you come across a problem that has forces that we have not included in our equation, you have to do the integral. So I will begin there. And so it says something along these lines. What is the work done by this, and I'll say other force, because it doesn't include gravity, it doesn't include a spring, and it doesn't include friction. Those were the three we focused. 4 if you count normal force, but it came out to be 0, so it doesn't show up in the equation. So if we come across any other forces besides that, which in this case we do, the gases expanding, we've got to actually do the integral. So let's put in the equation for force and the distance traveled. Now maybe a little picture of the bullet in a rifle might be useful. He'll be my barrel. He'll be the trigger. There we go. Very simple gun here. But the bullets will be somewhere in here, something like that. And so the bullet is going to move along the barrel length, which they tell us has a length of 0.6 meters. Okay? I suppose the first thing to do is to take the dot product. But this is probably the easiest step of all. Remember, we said a dot product would be the magnitude of the force times the magnitude of the other vector, which would be dr, times cosine of the angle between them. Well, in this case, what is the angle between them? 0, right? I mean, I think it's fair to say that the bullet moves along the barrel, and I think it's fair to say that the gases are pushing it along the barrel. And so that's why I would say this step is probably the easiest one, the dot product. And then I would have force, and then I would even replace dr with dx. It's very clear that it's moving along the barrel, and I'm going to call the direction of the barrel x. Okay? And of course, they don't say necessarily that the rifle is held horizontally in my picture. So my x doesn't necessarily mean horizontal. It could mean up at an angle. But I do know that my x is along the direction of the barrel. And I do know the force is along the direction of the barrel. Okay, now I can actually put in that equation. And so that equation is giving me the force. And that's why I picked this one. I thought it would be a good one to show the other term. And so they got a 15,000 plus, or was it a minus? It's a plus 10,000, and it's 10,000x, right?
Yeah.
And then minus a 25,000 x squared. And you could probably actually do this integral without even more thought about that equation. But that never sits well with me. And so I kind of like to think about what are they giving me. As you've heard me say, and it's worth repeating, I like to say, read the math. Don't just do the math. What's the meaning behind it? It'll often help you when you get in stuck positions of saying, okay, how do I solve this particular one? And so if I was plotting this force, I would first of all notice it is a quadratic, right? Which means it's a parabola. And it is a parabola concave down, isn't it? And I also notice, because of this term, it is not a symmetric parabola. That is, it is not centered around x equals to 0. It is shifted over in a positive direction. So it looks like to me that what they're saying here is when x equals to 0, the initial force is 15,000. And then I have a parabola that looks like that. Concave down, peaking here at some point. And as I give this more thought, it begins to make sense. Again, I don't know if I have to give it this much thought to actually do the integral. But what it's saying here is initially there is a lot of force. Well, that kind of makes sense if you know anything about a bullet and gunpowder. You have a shell, and you put gunpowder in it, and then you cram this lead bullet on top. And what happens is the gunpowder inside burns, and the pressure builds up until there's so much pressure it pops free. So as soon as it starts to move, right there at x equals to 0, there is already a lot of force on it. And so it starts with a lot of force. And of course, the powder is still burning, and the bullet is not moving very fast. So the pressure begins to build more and more and more. So even as the bullet begins to move down the barrel, the force continues to increase. So it starts with a lot of force, and it just gets larger for a while. But then, at some point down the barrel, one of two or both things happen. One, you stop burning gunpowder, you're out of gunpowder. Or two, you have, I got him. Two, the bullet now begins to go so fast that the burning of the gunpowder, although it may be still burning, doesn't really catch up as quickly as it used to the bullet. Have you ever ridden a bicycle downhill? And if you're riding a single gear bike, maybe when you were a young kid, what can happen is you begin to go so fast that your pedals, even though you're pushing, right, they don't really catch up to the gears in the bike, and you can't really push. And so even though you're trying to push, even though the force is there, if you can't catch up to the moving parts, you can't really push on them. Fair enough? And so that can happen on a bike. That can also happen on a car. I'm sure you've noticed on your car. Some of you maybe have a manual transmission where you have to change it yourself. Most of you probably have an automatic transmission where it shifts. But if you're in a particular gear and the engine begins to go faster, at some point the pistons are moving so quickly that you're not going to get much force from the engine. And so it's specifically designed to shift gears so that the engine doesn't have to go around so quickly, which is again why you have a multi-gear bike. When you're a little kid, you just had to live with it and just tried to catch up or just coasted down the hill. Now that if you have a multiple gear bike, you just switch to a higher gear so that you can, catch up to the motion of the mechanics without having your legs go around so fast. Anyways, that begins to happen. And so what happens is there still is a force, but it's not as large as it used to be. And in fact, at some point, which I would call right there, we reach that place where the bullet is going so fast that the expanding gases are going at the same speed, and the expanding gases aren't pushing on the bullet anymore. And you would actually start to get a negative force, really, if you went faster than that. Because now if the bullet went faster, then you would then create a negative pressure inside the barrel. Now, hopefully that doesn't happen for our barrel. Hopefully the 0.6 is before we get here. Otherwise, we're just slowing the bullet down. We sped it up, and now we're beginning to slow it down. So I can even see in the math, x equal to 1. You said x equal to 1. What do you get? 0. So this is 1 meter. So the force becomes 0 after 1 meter. And the barrel's not that long. As they say, the barrel is 0.6. So this bullet is going to be pushed up to this point. And then after that it exits. So we could have made the barrel even longer, right? And got more push out of it. We certainly would not want to make the barrel greater than 1 meter. 1 meter, now we start slowing it down. But if we really wanted to get the maximum speed out of this, we could have gone 1 meter. All right. Like I said, probably all that analysis isn't necessary to answer this question because this says just integrate, and so we're going to go from 0 to 0.6, right? That is the work done by the expanding gases. Integrate force and distance. So in my case, I would have 15,000 evaluated from 0 to 0.6 plus 10,000 x squared over 2 evaluated from 0 to 0.6 minus 25,000 x cubed over 3 evaluated from 0 to 0.6. Yeah. Oh, thank you. Yes, x. Yes. So 15,000x, 10,000x squared, yeah, x cubed. All right, so putting in my numbers here, I have 3,000 times 0.6 minus 0. I would add to that, and just to make my life a little easier, I'll just call that 5,000 right there. So that's 5,000. And then I would go times 0.6 squared. So that would be those two terms. Then I'm going to subtract off, I guess that would be 8,300. And then I would go times 0.6 cubed. And so I should get the number 9,000. 9,000 what? Not watts, joules, right? Because again, it's work. Work is measured in joules. You'll see that. Force times distance, right? Newton times a meter. A watt would be a rate. Yeah, would be power. So there's my 9,000 joules. And so I think I've answered A. I think B has the next part of this. B says, okay, now what if? What if the barrel was longer, 1 meter long? Oh, good. We've kind of already talked about that. How much work would be done? And compare it to A. I think you would agree that it would be more work. Right? You can kind of see then, going back to our calculus class, that we can visually represent an integral with the area under the curve. And so that 9,000 is represented really by the area under this curve. And so we are going to then do, and maybe I'll change colors here, we are going to do the integral a little bit more. And so we are going to have this much addition on here. It doesn't look like it's very much. And I think that's kind of the author's point here, is that even if you went ahead and made the barrel another 40 centimeters longer, which, you know, it's 60 centimeters. And so you're going to increase that by 2/3, right? A 66% increase in the length of the barrel. But it's not going to give us much more work. And it's not going to make the bullet go much faster. That last part is just not that significant. But let's see. What would change in this? It would just be the upper limit, right? And so I would have the 15,000 evaluated from 0 to 1. 15,000x. Can't keep forgetting that x. I would have the 10,000 divided by 2x squared evaluated from 0 to 1. I would have minus the 25,000 over 3 times x cubed evaluated from 0 to 1. And so this would just be the 5,000. I'm sorry, getting ahead of myself. 15,000. This is the 5,000. Because it would be a 1 squared and that. This then would be minus the 8,333. 8 1/3, yeah. And so if I take the 20 and subtract, well, 8 is 12. So I'll do a little more than that. I should get 11,667 joules of energy. And so, of course, as we expect, it is more. Perhaps not that much more, but it is more. The problem doesn't ask it, but I think this problem could be expanded by saying, all right, what are the speeds of the bullet in both cases? And see, looking at this big equation, haven't we just done that one there? And doesn't the bullet start from rest? For this simple problem, I don't think we need to worry about that term. There's no springs. Maybe the author doesn't do it because he doesn't say whether you're firing it up or down or horizontal. Let's just say we're firing it horizontal. So if you fire it horizontal, those are the same. We can cancel them off. There's no springs. I won't have to worry about that. There is no initial speed. Okay, so that term can go away. And so out of this whole equation, this 9,000 is right there. And on the other side of the equation, the only thing I have to worry about, again, if we don't worry about the friction as it goes down the barrel, is to say this would have to equal to 1/2 mv final squared, right? Now notice the work is positive. What did we say positive work does? Makes it go faster. And you can now see it in the equation. That if this number here is a positive, it's going to make this term bigger than that term. So positive work makes it go faster. So keeping that in mind and getting out my calculator, I can take this work of 9,000. I can multiply it by 2. I can also divide it by the mass of the bullet, which I think they said 100 grams up here. Now watch my units here. I'm going to divide by 0.1. And so again, let's go back to chapter 1. Watch your units. Okay. Our work is in joules. Remember what's inside of a joule is a newton. Remember what's inside a newton is a kilogram. Okay. And then if I take the square root of all of that, I get a speed of 424 meters per second. And so typical speeds of a rifle, and so probably these are reasonable numbers. Over here I can do the same logic. I could say this would equal to 1/2 v final squared also. Now I have a bigger number here. I have 11,667. So if I multiply it by 2 and divide it by 0.1 and take the square root of all of that, I get a speed of 483 meters per second. So again, notice it is a positive amount of work that does make it go faster, and it is more work than part A, so I would expect more speed here in part B than in part A. And notice it's not that much more speed, as again to be expected. It's just a small amount of work. It's on the curving edge of this function. And so that, like I said, thought would make a good second problem. Well, let's try another one. I think what makes a good third problem here, and involving a spring. Although in this case, it's a dual spring. I thought it would be a good one. I was a little hesitant to give you one with a dual spring without giving you a single spring, but I think you're ready for it. Let's throw it out there. Let's do both of those. Let's give you a spring, and not just a spring, but 2 springs. In fact, it might be better to see the picture. It's number 21, but the picture is on the top of the next column. And so let me scroll up to the top of the next column. Here's what they have. A dual spring system you see a lot. This one happens to be describing a railroad switching yard. But you see them on big trucks. Even your mattress probably has a dual spring system. Here's the idea, that when something comes in, there will be a spring within a spring. Because if whatever is coming in, like in this case a train, and it is moving slowly, so let's say we're, a Union Station in LA, okay, and all this enormous amount of freight comes into the LA harbor, and then you bring it up and you put it in the Union Station, and so the workers there say, okay, that train is going to the East Coast, put it down there. That one, oh, that's going to the Pacific Northwest. That's going to the South, put it down this track. And so they separate off. All those TVs are going to the East Coast. Here's another boxcar of TV. That's going to go to the South. Here's another boxcars of TV. That's going to go to the Pacific Northwest. So all these TVs that probably came in from China, now we got to separate them and send them across the country so people can buy TVs. And what would we do without all these TVs, right? So as these trains are coming in, we got to put them down these switch yards. Okay, and so this train is going to be being made. And so here first comes these TVs, and then I move the TVs to the other one. The next set of trains might be, I don't know, what else comes in? Computers, all right. So we get a boxcar of computers. So we got to send one boxcar to the East Coast and one boxcar to the Pacific Northwest and another one to the South. Anyway, so we're making our train. And eventually we're going to have this really long train of all this merchandise that is going to head off to someplace into the country, all right? And so to do that, we send this rail car down here. But look at this. As we send it down, we want to stop it at the end of the line so we can build up the train. Now, if it's moving slowly, you don't want to put a big force on it, you want a little force on it. And that's what the first spring would do. The first spring is probably a weaker spring. It is one that would be compressed just by itself. But on the other hand, if this boxcar is coming in kind of fast, then don't you want a large force on it? And so if it is coming in fast, what will happen is this first spring will stretch or compress real easily. Then it will make contact with the second spring. Now the second spring will begin to compress. In fact, both of them will be compressing. And the second one is probably a stiffer spring, a higher spring constant. And it's designed then to stop the fast-moving objects. And so the same reason you have a mattress that is often built this way. Because sometimes light parts are on the mattress, like near your feet. And so you want it to kind of cushion in real easily. But on the other parts, where your main body is, you want the spring to hold up a lot of weight. And so you want something to hold the light forces, but something to also hold the heavy forces. If you made it just with a single spring, then the places that are heavy would kind of sink in, and you would sleep all night kind of with a dip. Your head would be high, your feet would be high, and your body would be low, and you'd probably have a stiff back when you woke up in the morning. And so that dual spring system is nice for that. Big working trucks are like that, because sometimes you have the big truck loaded with, say, gravel, and other times you don't have it loaded. And so when it's unloaded, you want the wheels and suspension operating on a spring. But if you start piling a lot on, then the truck goes down. You want it to catch another spring that's going to hold the heavy weight. Otherwise, it would go so low that the wheels would rub. And so again, most of your heavy equipment will have this dual spring system. All right, so I think you got the idea of step one, what physically is going on. Let's read this one in more detail. It starts on the bottom of this, but 21 here says that we have a 6,000 kilogram freight car, and it's rolling along the rails with negligible friction. All right. The car is then brought to rest by a combination of two coiled springs as illustrated in the figure we were just looking at. Both springs can be described with Hooke's law. The first one has a spring constant of 1600. The other one has a spring constant of 3400. After the first spring is then compressed 30 centimeters, it then makes contact with the second spring that acts with the first spring. To increase the force, as additional compression is required, as then illustrated with the graph. And so the author is trying to help you out here understanding that the first 30 centimeters of compression is just that first spring. That is spring constant 1600. But after that, then you're compressing both springs. The one with a higher spring constant and the first one, which has already been compressed quite a bit. And so it's saying now your force is a much larger increase for every meter you compress it. Yeah.
Did you just add the spring constants?
Glad you asked. Let me build up to that. But let's finish the question here. It says the car comes to rest 50 centimeters after making contact with our two spring system. All right. So let's talk about this one here. I'm going to use this one in its grand finale form here, although, again, this is a simpler problem. It doesn't have all of them. But I would say that what's not well illustrated here is that I would have two springs. That was your question, right? And so if we go back and look at how did we get that equation up there, this term right here, didn't that come from the spring? So how would this be modified if we had two springs? Well, I guess I'll write the first term, mgy initial. And let me go and write k1 x1 squared. But if you had two springs, wouldn't you just be saying the total force then is spring 1 plus spring 2? So wouldn't you just have another term that looks just like the first one? And so that's how I'm going to expand our little equation. You might say it's fitting under this category as other. I already did one integral, which gave me the first spring. And now I'm going to do the other one. But I picked this one because it illustrates something important with Hooke's law. Let me emphasize it again. We did it last time when we were deriving it. The Hooke's law, maybe I should put it over here, minus kx. There was something important about that equation. What was it? Where does x equal to 0?
The spring is untouched.
Yeah, untouched. The word we like to use is its natural length. It's not stretched, it's not compressed. Okay? And didn't we get this equation by using Hooke's law? So let me emphasize it. Freedom of choice, but once chosen, it has power over you. All right, so you're going to use this equation? Fine, I recommend that you do. Where did it come from? That equation. What is that equation saying? X equals to 0 where? That's the natural length. So in other words, x equals to 0 has already been chosen for you. And it's even a little more complicated than that. X equals to 0 is different for the different springs. Right? But other than that, everything falls right in line. And that's what I'm trying to get you to see, which was your question. How am I going to deal with the two springs? I would say deal with the second spring, just like the first one. Take Hooke's law, let's integrate it. That'll give us a second term that looks just like the first term. But I also need to remember where it came from. That's why going through these derivations, I know students can often gloss over, oh yeah, teacher's going through some proof, I'll just wait till we get to the equation. But if you wait till you get to the equation and all you do is memorize the equation, you will run into troubles at times. It's not as simple as just plugging and chugging. Sometimes you will get it right, sometimes you will get it wrong. It's why if you just plug and chug, you will do okay. You'll get an okay score. You'll transfer to an okay school. You'll have an okay career. You'll make an okay salary. You'll meet an okay spouse. You'll have okay kids. All right? But to really thrive, to really go beyond that, to actually do something new, to invent something that hasn't been done before, to make that multi-billion-dollar product, you got to understand the physics behind it. There is no equation already done. You've got to find that equation. You've got to know what can and can't be possible with the laws of physics and apply those laws to see what I can make happen or how I can make it better. And so that's why these derivations we go through. And in this case, it is crucial that you understand that I can just simply put another identical term, just like the first one, but I need to realize that the position of x equals to 0 for this one is the natural length of the second one, and that is at a different point than the natural length of the first one. But other than that, I'm good. So let me keep going. Over here, I would put the 1/2 mv initial squared. Let me skip the other because there is no other forces other than that second spring involved here. So I won't even include that in the equation. I'll keep going here. This is the mgy final. This is then the 1/2 k1 x1, and I should put final squared, which I guess reminds me that over here, I guess I should put initial and initial. Initial. And over here I should put final. So final vertical position, final position of spring 1, final position of spring 2, final velocity of the boxcar. And I might as well just put a 0 there right away too, because they did say that go ahead and neglect friction. Okay? In fact, maybe I'll start with these two terms. It's worth saying it again. That's what we call the gravitational potential energy. When we worked out the equation, we were required then to call up positive and down negative. But we were not required where does y equals to 0. So we have that choice. Any preference? I think it's fair to say they're trying to imply that that boxcar does not go uphill or downhill. Fair enough? So let's call the ground 0. And the initial height is 0. And then after it compresses the spring, its final height is still 0. And so some of you, I could hear saying that under your breath right away, that there's no point including that one into our equation. But I wanted just to talk about that one again because I think the contrast between the gravitational potential energy and the elastic energy is a good discussion to have, because the gravitational potential energy, the direction of up being positive has been chosen, but the origin has been not. But for the springs, the origin of x equals to 0 has been chosen as the natural length of the spring, but the direction has not been chosen for us. And so we got to be careful on these two. They're easy to mix back and forth. Okay? So let me start putting in the terms I know. For example, before the boxcar gets here, what is what I would call x1 initial? Isn't that 0? Right? The spring is just sitting there at its natural length. I do not have the freedom to choose where x equals to 0. That spring kind of shown in this picture, is at its natural length. It is not stretched, it is not compressed. I have no choice but to put a 0 there. How about spring number 2? It's also 0, same logic. So simply put, all these energies that are initial energies, they all go to 0 except the obvious one, and that is the motion of the boxcar. And so this is a 1/2 times, did I see 6,000?
Yeah.
And initial speed, did I? Or is that what we're looking for? Yeah, okay, so the initial speed is what I'd like to solve for. Okay, so again, long discussion. I would expect by the time the test comes that you would probably quickly just say 0, 0, 0, blah. In fact, on the test, I guess I wouldn't even expect to see these crossed out or those being 0. Hopefully, after you gain some experience, those will be so obvious to you. All right, but that's the initial kinetic energy. The other side of the equation then. Well, let's talk about spring number 1. I might need to scroll down. Didn't they say that was 1600? Okay. So the spring constant is 1600. What is the final position of spring number 1? Now the problem says the car comes to rest 50 centimeters after first contact of the two-spring system. So let's see, if I see the picture right, the first 30 would definitely compress the first spring by 30. But then as it moves 20 more in, it's still compressing the first spring. All right, so how far is the first spring compressed? Yeah, it's 50 centimeters. Now let me watch my units here. We're back to chapter 1, right? That this right here is in units of newtons per meter. So I need to make sure my distance is in meters so that when I square it, I will get units of joules. I will get a meter downstairs canceling with a one of the two upstairs, and I'll get a newton per meter. So to get this in joules, to match meters per second, watch your units there. In other words, buried inside a joule is meters, seconds, and kilograms. Use those units. If they give it to you in centimeters, switch it over to meters, which they did. Oh, by the way, would this be a positive or negative 0.5 meters? Okay, you say it doesn't matter. I agree. Why doesn't it matter? Okay, mathematically I'd say it doesn't matter because I'm squaring it. Okay? Physically I'd say it doesn't matter because, again, back to Hooke's law. Hooke's law is valid for which either way you want to call positive and negative. So I still have the freedom of choice to call one direction positive and one direction negative. So then it's just a matter of my choice. What do I want to make? And you can see mathematically why I have that freedom, because it won't matter mathematically because I'm going to square it if I call it the negative direction. I won't. I'll call it the positive direction. So let me call that direction the positive, and that's why the 50 comes in here. I'll continue on. The second spring. 3,400? Do I need to scroll back? Okay, so the second spring at a spring constant of 3,400. And what is its final position? It's 0.2, isn't it? And that's another reason why I liked this problem. Again, not only did it give you that second spring, which was a little harder than just one spring. So like I said, I kind of questioned if this was a good one to throw at you, because we hadn't even done one spring. Now I'm throwing two at you. But again, it illustrates what I'm trying to say is, what does X in that equation mean? X is how far the spring is either stretched or compressed from its natural length. And spring number 2 is not being compressed the whole 50. So we got to read the problem, we have to understand the physical problem, and then we got to know what the variables mean. So in other words, we have to read the math and then you put it in. And again, maybe that's so obvious, but let me do the last term. What then is the final speed? 0. So the final kinetic energy is 0, because they say this is where it comes to rest. The car comes to rest at 50 centimeters. They made it very clear it was at rest. And so now you can see that we have an equation. It's got a lot of terms in it, but there's only one unknown. And nothing's better than one equation with one unknown. No system of equations I have to solve for. In fact, before I even begin to solve it, I might multiply everything by 2, so I don't even have to worry about halves. And so here I get 1600 times 0.5 squared. I'll add to that 3400 times 0.2 squared. Once I get that number, I will then divide it by 6,000. And once I get that number, I will then take its square root. And so 0.3 is the speed. And so not much of a speed, as it shouldn't be much when we're just in a switching yard and things are moving around real slowly. It also is stopped by a dual spring system that's got some pretty high spring constants, but not that high, and we compress it. All right, oh, good. How are we doing on time? How about we try another one here? My 38. I've got listed as a good one to do next here. And this one involving some gravitational potential energy. All right, let's read that one together. And maybe I'll clear the board here first. But again, let me emphasize, I'm not going to do anything but work with that equation for these 2 chapters involving the energy. Now, seldom will I have to use all those terms. But again, I was trying to condense the lecture and just kind of give you the whole grand finale in one shot and say, okay, this is the big picture. Not all the times do we have every term involved, as you can see. And this is a good example of that. Here we have a 400 Newton child is in a swing that is attached to ropes that are 2 meters long. Find the gravitational potential energy of this child and Earth system. And then it says relative to the child's lowest position. When A, the rope is horizontal, B, the rope makes an angle of 30 degrees from the vertical, and C, when the child is at the bottom of the circular arc. Okay, so maybe I'll begin by, again, just trying to understand the physical picture a little bit better. Usually drawing a picture kind of helps. Maybe this is the ground. And so the swing set itself is anchored up there. Trying to give it some three-dimensional look here, but there'll be a rope coming down and another rope coming down. There'll be a little swing. I think they told me just the length of the rope, right? Not how high is the swing off the ground. They also told me the weight of the child, not its mass. My picture doesn't necessarily have a child in it. So let me put a child there. All right. The weight of the child is 400 newtons. I don't know if it's needed, but the mass would be the weight divided by G. It doesn't look like I'll need that, but I'm going to get that number nonetheless. So there's the 400 divided by 9.8. And so this child is 40.8 kilograms in terms of mass. Okay. And then the child swings, and it looks like in A, they are saying, what would happen if here's the ground and the child is horizontal? It's a heck of a swing, but maybe it's a big kid, so big kids like to do that kind of thing on the swing. But B says, well, what happens when the child is angled at 30 degrees? Now, did it say 30 from the vertical or the horizontal? Yeah, from the vertical, okay. And then C is saying, well, at the bottom of its circular arc, so here. Well, I'll start with the question they asked. They said, what is the gravitational potential energy? Now, which of these terms is gravitational potential energy? Yeah, the mgy. Okay, so let's do A first. What they're really saying is find mgy. And I haven't been really using a symbol. If you look in your book, your author will use the symbol U sub G. The U for the potential energy, and then the G because this is the gravitational potential energy. He uses a U sub S for the spring. He uses a K for the kinetic energy. I just put those all up here. But I thought I would use this as an opportune time to say I'll call that U sub G, and that would be initial. I'll call this U sub S for the spring. I'll call this K for kinetic. I've already called this one heat, but let me call that kinetic. That'd be final. That would be called U sub S final, and that would be U sub G final. And so part of the reason I picked this is I thought I should make sure I give you the symbols that the author's using. You'll see that as you read it, and you might come across it in some of the problems. Okay. And he's asking just about, not all the energies, so not the kinetic energy, but just the potential energy, which is that mgy. Okay. And he asked for these positions. But notice he says something in here that I want to make clear. He says relative to the where is it? How does he phrase it? Relative to the child's lowest position. Put another way, where does y equal 0? And so I'll say it again. We have that freedom of choice, right? With the gravitational potential energy, we have to call up positive and down negative. That was the condition when we did the integral. However, we can pick y equal to 0 anywhere we want. The first example I did was illustrating picking y equals to 0 at some point. And so you can pick it anywhere you want. And then everything is measured relative to that point. In this case, you don't get the freedom of choice. He's telling you where you're going to make your choice. And so he is saying, make your choice where? Right there. And again, I thought it made a good problem, and I'm sure the author is too, because he's trying to say you don't have to pick the ground equal to 0. And I think I've illustrated that once already, and this is probably just more of the same. That you can pick y equal to 0 wherever you want. Since we don't know how far it is from the child down to the ground, don't even put the ground in your picture. That's just going to throw you off. Pick what you do know, and you do know that there is a low point. You don't have to pick the lowest point, although it's kind of nice to pick the lowest point because then everything's positive from there on. Okay, but it's your choice. Well, I would say in most problems it's your choice. In this case, he's telling you what your choice is. All right. So your choice is the lowest point. All right. So in this case, with the child over here, meaning that this is the lowest point right there, y equals to 0, means the child is 2 meters up, and for that matter, it's 2 meters over. So what is the gravitational potential energy here? Well, yeah, the weight of the child is the mg, so I'm just going to put 400. What's y? Is it 2 or is it 4? How come it's... What about the 2 that's horizontal? Doesn't matter, right? That's what we saw in the integral. The gravitational potential energy is the vertical height only. And again, this makes a good one. It illustrates that. The work done is the component of the force in the direction of the movement. And so the fact that the child moves horizontally does not contribute to the work or to the energy. There is no gravitational force horizontally. So all of this is just to make sure you illustrate that just because the child has moved horizontally, that's irrelevant. The question is, how high is the child? And as you guys said correctly, the child is 2 meters up. So with that in mind, I would get 800 joules. I would get the weight of 400 times a height of 2. That's it. It's really that simple. 400 times 2 is 800. And as you gain experience, I guess I would have expected you to answer that probably in 3 seconds or less. Like 400, height of 2, 800. How hard is that? But there's a lot behind it. And that's what I wanted you to see. You can pick y equals to 0. You don't have to worry or pay any attention to the horizontal motion. Well, let's do B. Calculating again the gravitational potential energy. It is mgy. Now the mg is the easy part, 400. They gave that. Okay, I get that. How high is the child? Okay, I heard 2 cosine 30.
Two minus.
Yeah, it's not just 2 cosine 30. Let me draw the picture here. Right, if this swings back here, then if I make a triangle, this part right here is 2 cosine 30. But that's not the height of the child. What's the height of the child is that piece, right? And that piece would be the whole length, 2 meters, minus this length would give me my y. And so again, dealing with gravitational potential energy, it's not supposed to be hard. And I'm trying to illustrate, you don't have to pay any attention to the horizontal motion. That's what's going to make it easy. You do have to pay attention to the vertical height, and then of course you have to do your geometry to make sure you're at the vertical height. So let me clean this up a little bit. As you guys said, it would be the 2 minus 2 cosine 30. That would be the vertical height. And so if I take 2 minus 2 times cosine of 30, I get a height of probably about 27 centimeters. Then I can multiply it by the 400 and come up with 107 joules of energy. And given everything we've already said, then C should be the easiest one of all. And once you understand, you kind of even question, why would he give you such an easy one? But he wants to make sure you understand that you can measure it relative to something, and you can pick that. And in our case, he's saying pick it to the lowest part on the swing. So when he says in C then, what is the potential energy of the child at the bottom of the circular arc? Answer? 0. And so the potential energy is 0 because what is your y value at that point? 0. And why is the y value 0 at that point? Because you picked it. And be careful here. What if the child jumped off the swing and got on the ground? What would you say? What's negative? Y. So their height is what? Negative. What about their potential energy? No. Isn't it negative? mgy? Anything wrong with negative energies?
Can't have negative energy.
I can't? Why not?
Can't have negative.
Why can't I have negative energy?
Can't get rid of energy. Conservation of energy.
No, there is nothing wrong with negative energies. And that's why I thought I would take a moment and pause here. Remember, your energy is relative to where you call it. What if we would have called y equals to 0 up here? What would that say when the swing down here? Wouldn't have that said that we had a negative 800 joules? There's nothing wrong with negative energies. Negative 800 joules just simply means that this point is 800 joules less than that point. That point is 0, so this is negative 800. Or we could switch it around. This point is 0, and that is a plus 800, which is why the ground would be a negative number. You don't have to call the ground 0. Even if you did call the ground 0, that just means up here on the swing it is something greater than 0, and up here at the top of the swing it is 800 more than that something. You may feel good that these are all positive numbers, and then you realize that somebody digs a hole and the child crawls inside. What's the potential energy of the child now? It's now negative. And so a little subtlety in here is illustrating that the choice of 0 energy and the choice of 0 height is a human reference. Physically, up here is more energy than down here. But you could have negative numbers. And if it is really far down, it's just more negative than here. That's just saying that is less energy than here. Nothing wrong with negative numbers. And in fact, there are many times where using only negative numbers is actually kind of convenient. You can see that if I picked y equals to 0 at the top, wouldn't the child always have negative energy? Now, I would say for this problem, that's not very convenient. But when we get into chapter 13, you will see, as we deal with rocket motion, it's going to be really nice to deal with negative energies. There'll be a real big advantage. It'll drive you crazy, and I will come back and I'll say, hey, remember when we were working in chapter 7 and we talked about 0 energy and there's nothing wrong with negatives? We'll revisit this in chapter 13. And we will deal with lots of negative potential energy. And I will say then, there's nothing wrong with it. And I will point out what the advantage is, even though I do think it gets a while to get used to. You're like, what? No, I don't like those negative numbers. But I'm sure by the end of chapter 13, you'll conclude too. You'll go, you know what? I really see why NASA likes these negative numbers. This is really nice dealing with the rocket and planetary motion and dealing with the negatives. So more on that when we get there, but it is really nice. How about we move on here? How about 57? '57 I thought would be a good last one to do in this chapter. Because now we've done quite a few. We've done ones with springs. Actually, our spring had a double spring. We've done potential energy. We've done some kinetic energies. I think this has a little bit of everything in it. So let's read this one. Here we have a ball launcher on a pinball machine. Today's video games. You guys know what a pinball machine is?
Yeah.
All right, okay. So you pull the little trigger back. There's a little spring in here, launches the ball to the top, and the idea is the ball rolls downhill. You got the little flippers, and you're trying to keep the ball up and rack up points. Gravity's trying to make it go past the little flippers from hitting it up. All right, so we have a ball launcher on a pinball machine that has a spring constant of 1.2 newtons per centimeter. Don't fall for their little sucker bid on their units. Pay close attention to the units. You would, of course, do that on a test. You wouldn't let the teacher trick you with the units like that, right? Good. All right. So there is a little unit conversion that we need to be careful with here. It says the surface of the pinball machine is inclined at 10 degrees. So there it is. There's the surface of the pinball machine angling up at 10 degrees with respect to the horizontal. The spring is initially compressed 5 centimeters. Watch our units here. So basically, they're going to take your hand and go pull back 5 centimeters. Find the launching speed of the 100 gram, not kilograms, so you got to be careful there. The 100 gram ball when the plunger is released. Go ahead and ignore friction. And also, don't even worry about the mass of the plunger. Because obviously when the spring pushes, it doesn't just push the ball, it's got to push the plunger also. So, don't worry about the plunger. That's just the ball itself. Okay. And so, what is the launch speed is the question. And so you can see that there is a spring involved. You can see that there's gravity involved. And obviously there is kinetic energy involved because that's the question. And so let's work on all of these together. I'll start with the first term as always. This first term is the gravitational potential energy. Now remember for that one, we have to call up positive and down negative. Okay, so I'll keep that in mind. But we have that freedom to pick y equals to 0 wherever we want. Where would you like to pick y equals to 0? This is what, 57? So here's kind of the incline. I guess I will say this is when the spring is compressed like that, and maybe changing colors here. Then I will have the plunger up here when the ball is released. And if I understand this problem correctly, this distance that we pulled it back is the 5 centimeters. So I grab the handle, I pull it back 5 centimeters, and I let it go. So I'll ask you, where do you want to call y equal to 0? Maybe back here where it's in the launch point? In fact, that's what I'll probably call the initial spot here. Why don't we say, here's what's going to happen. You're going to pull it back. So in other words, initial is not before I pull it back. Initial is after I pull it back and I'm holding it. Let me call that the initial. So that when I let it go, the force is not coming from my hand. So I won't have anything like this. If I called my initial before I pulled it back, then I would have some kind of outside force from my hand. So let's call initial the moment where it is just getting ready to be released. And the final is after my hand releases the plunger and the ball has then moved up 5 centimeters and is taking off.
Doesn't that mess up the next term?
Mess up what?
For the spring? FKX, doesn't XI for the spring have to be when the spring is relaxed?
I'm glad you bring that up here. Let me answer that 2 ways. Watch this. Notice that this equation says the energy, and we wrote it as energy initial equals energy final. But please remember, it's more than that. It is energy at one moment is equal to energy at the next moment. So my definition of initial doesn't have to be before I pull it back. My initial can be anywhere. My initial could be after I pull it back, which I'm going to use. It could be when I pull it halfway back, which I don't want to do that for the same reason. I got to then incorporate how much my hand is pulling on it. My initial could be 20 years ago, and then all the pieces that went together for the last 20 years, which obviously I don't have enough information to answer that. So I can pick initial at any moment I want. Your question's a little different though. Your question then goes on to say, if you pick initial after your hand has pulled it back, what are you going to do about the X? And maybe it's best until I get to that term, and I'll bring that up, but that X has a meaning, and it doesn't matter where in the position, whether I pulled it back, whether it has come all the way up, whether it is halfway back, that X has a meaning, and I could put the meaning in there. So let me build up to that, but I want to illustrate my definition of initial is anywhere I want. My definition of final is anywhere I want, because it says the energy at one moment is equal to the energy at the other moment. So my beginning moment is going to be after my hand has pulled it back, but my hand has not released it. And I thought I heard some of you saying that that would be a good place to call y equals to 0. So I will. It's not the only place. You have that choice. But what makes it a nice choice is, what would that do to this first term? Makes it 0. And so that is what I would suggest. I would suggest you call y equals to 0 either at initial or final. So one of those two terms is 0. Most of you will probably feel the most comfortable if you call the lowest point y equals to 0. Which, in this case, the lowest point and the initial point are the same. And as you pointed out before, if you do call the lowest point y equals to 0, then you only have positive energies. However, let me say it again. Don't get too worried about negative energies. There's nothing wrong with them. And in the future, in chapter 13, we'll actually appreciate those. So I hesitate by encouraging you to say to avoid negative energies, because we're about to get, although not for a couple more weeks, into problems where we're going to encourage writing things with negative energies. All right, but on to here, I would say my initial potential energy is 0. This is really then the question you are asking. What about my spring?
You just go X minus 5.
Let me start with the easier one, the spring constant, before I get to the X. Didn't they say the spring constant was 1.2 newtons per centimeter? All right, so since work and energy are in units of joules, and joules have meters in them, let's change our centimeters to a meter. So before I continue, let me do a little conversion. Going back to chapter 1, what does centa mean? And so there's my unit conversion, right? Centa means 100th, and so that means I have 120 newtons per meter. So switching this into units of newtons per meter, I would have 120. So it's 120 newtons per meter. That's my K value. Now let's talk about that X. This is back to Hooke's law. It's worth emphasizing it again. If we're going to use Hooke's law for a spring, where does X have to equal 0? We don't have that choice, right? It was part of the equation we used. So where does X equal to 0 on a spring? Its natural length. Is the spring starting at its natural length? No, it is compressed. How much is it compressed? 5 centimeters. So I will put 0.05 meters. That is how far it is from its natural length when I am starting. I could ask this question, is it a positive or a negative? Yeah, and we're back to the same discussion we had with the railroad cards. You have the choice to call that direction positive or negative. So what would you guys like to do? Pull it back. Do you want to call that the positive direction or the negative direction? Negative direction? Okay. So this is a negative 5 centimeters squared. And of course, mathematically, you can see if you're going to square a negative, it won't change anything mathematically. So your choice, but let's choose it now. So I'll say it again, when you're working with springs, you don't have the choice of where x equals to 0. Or I should say it differently. You already made the choice. When you got this equation, the 1/2 kx squared, you, whether you realized it or not, made a choice of where x equals to 0. And that's why I keep emphasizing it. Because I've seen students struggle on the test this way. They get all confused of where x equals to 0. Because they want to pick it. But they want to use that equation. You can't have it both ways, right? You want sleep, but you want to take this class. You can't have it both ways, right? It's one or the other. Once you take that choice, it's going to consume all your study time, okay? Well, actually not just this class, but by the time you put this class together with the other millions of things you have in your life, you probably won't get any sleep. That's why, like I said, I think the students who take this class in the spring have a little nicer advantage because they got that spring break in the kind of the middle, right when we get into some really hard stuff. So you can either get some rest on spring break or you can study up, because either way it's going to hit real hard after spring break. But there is what I would do, and I hope I now have finally got to your question. How am I going to treat the x? And so there's my initial. I'll keep going with this. What would be the initial speed? 0, right? So I kind of imagine pull this back and I'm holding it there. No velocity to it. Other forces. Well, let me just kind of get rid of those. Other forces, you know, aren't here. We don't have like the gunpowder burning, so I'll just kind of skip that one. And then I'll move on to the other side of the equation. When the ball gets launched then, what's the gravitational potential energy? Well, M, G, and then the Y. And the Y is not 0, but let me put the M in there first. What'd they say this was? 100 grams? Again, watch your units. I'm going to put 0.1 kilograms. I'll put G as 9.8 meters per second squared. But what's the height? Yeah, good. You guys see it. You can make a little triangle here. And we've been making these triangles since chapter 3, right? That what happens is you can figure out this height right there. That is y final. The hypotenuse of the triangle is the 5 centimeters. So to get the vertical height, I would want the opposite of 10 degrees. So this comes out to be then 0.05 sine of 10 degrees. Plus or minus? It's plus. Why? We have to call up as positive, right? In the derivation of this equation, we have to call up as positive. We don't have that choice. Okay, so I'll say it again. Using this equation, you are choosing which way is positive. Okay, up. Using this equation for the spring, we are choosing x equals to 0 to be its natural length. Okay, gotta see that in the derivation. And of course, I've emphasized it 1,000 times today, so as we move on, I'll emphasize it a lot less. But you hopefully got that idea in all of there. Oh, let me go on to the next term. I'm kind of out of room on the board here, so let me just put it underneath here. But this would be the spring. What's the final position of the spring? Yeah, it stretches back out until it gets to its natural length. So I'm going to put a 0 there. Next term. This is the final speed. 1/2, and then it's 1/10 of a kilogram for the mass, and then its final speed squared. Which is that question? That's what we're after. What is the launching speed of this? And then the last one would be any friction or heat that is going on. And did they say anything about that? Oh yeah, they said the friction we can neglect. And they said the mass of the plunger, so I don't have a kinetic energy for two objects. The next example I do, but we'll be out of time for today. So on Monday, the next example I do, let's have two objects. And you can imagine what two objects would be like, just like two springs. Wouldn't we just have then two terms to deal with? Exactly. And that's what we're going to do real soon. But to finish this problem, you can begin to see that I know that number, and I know all of those. And again, nothing better than having an equation that you know everything but one variable so that you can solve it. And so starting with this one, I will go 1/2 times 120 times 0.05 squared. And so that's 1.5. Moving this to the other side would be a subtraction, so I will minus 0.1 times 9.8 times 0.05 times sine of 10 degrees. And so that would subtract off there. Multiply that by 2, divide by 0.1, and take the square root of all of those. I get 5.46 meters per second. And I feel like I hit a wrong number.
You said 1.5, isn't it 0.15? Is it, on the left side?
I think I just said it wrong. Let me scroll up here. Oh, this model doesn't scroll up. But yeah, that's 1.5.
0.15.
Oh, 0.1, let's see. 1/2 times 120 times 0.05 squared. 0.15. Okay. I think I did hit something wrong. Minus 0.1 times 9.8 times 0.05 times sine of 10 degrees. Then times 2, then divide by 0.1. 1.68 meters per second. Well, I should check. Anybody else do this? Yeah, you got that number? Yeah, okay. So, yeah, I suspected I hit something wrong there earlier on. Anyways, there's the number. All right, well, we're done for today. And I've done all the examples in chapter 7.